Okay, so I assume you guys can hear me. Just somebody give me a yes. Good. All right. What about this? Can people see this here? I might need to I need to figure out how to make the font bigger. So the table was can people see that? I mean, how big is it? Is it big enough? So I need to make it bigger? Big enough to see. Good. Okay, very good. All righty. So the example that we were dealing with was basically, okay, so we have two tables. We have V, and this will be then just basically node. So we have edges and vertices. And then we have, let's see. So now we have the database instance that represented that one graph. Might as well just kind of show that then. So that would basically this. I'll this is kind of like a standard, a little bit kind of a standard notation. A, B, E, A, C. Actually, it was B, C. B, C, E, to let's see, E to let's see, B, E, and then E, E, A. Okay, so that was kind of showing that, drawing that kind of graph out. Now, the issue that we want to kind of address here is the question, we want a reachability relation from to. So what can be reached from what? Now, what you'll see then here is that what's that going to be? So we can maybe just kind of like think of it intuitively. How let's build this up. Let's build up this I think will show kind of the example of recursion as we build this thing up. All right, so I can reach B. Okay, so if there's an edge that goes from A to B, then is it correct to say the following? That is that there is, if we want to talk about reachability, then all of these should be reachable, right? Is that true? Is it true that if there's an edge that goes from A to B, can I also reach B from A? And the answer is yes, of course. So as we define, if we're going to use like relational algebra, let's just say R equals E, right? So what this is basically saying, it's saying that copy everything from E into R, right? What is there? Oops. Anyways. All right, so this is one part of the definition of it. But notice here that there's another thing. That would be the following. That is that I can also say that if something is, if there's an edge that goes from to from, okay, and then let me just do a big cross. That's our Cartesian product with R to from, and then I'm going to do a what I'll say, the I guess, what is it, it's a I think it's a sigma, right? Sigma, it's a lowercase sigma. Oops. Sigma. Now so this is the join condition right here. So this right here is our Cartesian product. And now I just basically want to say the following. I want to say the condition under the sigma here is going to be E dot.
Oh Lord. Oh Lord.
I think I hear some people. I do something kind of stupid here. I hear people laughing.
No.
People are laughing at me. That's fine though. I don't mind being laughing. So hey guys, I mean, there's somebody who's got. Let's see, who needs to get muted here? All right, someone needs to get muted. Guys, I don't know if you're hearing, but you need to be muted. Let's see here. Who is it that needs to? Could everybody mute their microphones? Okay, I think that maybe now. I hope they didn't give themselves away. You know, I don't want this. I don't want this video here to become viral. Like they said something that was not. They probably said, "Yeah, Minag is such a fuck idiot. He's an idiot." No, okay. Anyways, it's okay. I won't hold that against anybody. Okay. Anyways, okay. Sigma. What do we have here? So if I say E is from and to, and then R is from and to here. So if I say now that basically E dot to equals R dot from. Okay, so what is this doing then? So this is the sigma here is the select in relational algebra. You guys see what's going on here? Roughly? Yeah, I can mute them. I just couldn't find them. Unfortunately, when I do a screen share, this is another thing that's stupid about Zoom is once you do a screen share, you lose. You have to. It's much more. You lose your control panel, and they haven't changed anything. And I did an update recently of Zoom, but I just think that their code base is probably just awful, and they can't change anything. That's when things don't change. I just assume like it's just because they don't dare touch the thing. All right. Okay. Now, do people see how this works here? Let's see here. Should I explain it here? Because this is it. Okay, R equals E. That's what this is right here. Okay. Now we have an R, right? And there's an R here. And notice that R is dynamic. R is recursive. It's going to grow and grow and grow until it can't grow anymore. And how it's going to grow is this is the recursive definition. This is what's making R grow. So we take the current R, which is this right here, and then we take the current E. And is there any, oh, I'm sorry, I need to also say a pi. And then, so what's being selected here is E dot from R dot to. Okay. So what I'm going to do then is let's just kind of do a simple example here. So I have E and I have R. So if this was just static, if R was just static, then you guys could compute what this R prime is here. It's easy to compute what R prime is. R prime then is just going to, like, what's an example of something that's in R prime? Something in R prime would be basically, okay, can I get from A to B and B to C? So this is a member R prime, okay, A to B and B to C. So A, C is in R prime. People see that? I hope. Among other things. Also, R prime equals A, so A to B and B to E. So it also equals AE, right? And what else does it equal? All right, B to C, does B, okay, B to C, B to C. So it actually does have in it B to C. No, I'm sorry, B to C, the C, no, C doesn't go anywhere. B to E, does E go anywhere? B goes to, okay, so then it means that an R prime will also have R prime B goes to E and E goes to A. So B goes to A winds up being an R prime as well. I think that actually might be it for R prime. Okay. Now, because the thing is recursive, it's not R prime that's being defined here, it's R. So what happens here on this recursive step is that we're going to pile in these fresh results. So now our R is equal to this. Okay. So now we're going to do the next step. So now we have, here's our R and here's our E. So we have E goes to B and we have B goes to E. So that's a fresh, I'll go back to R prime here now. That's a fresh new tuple. R prime goes from A, I'm sorry, A goes to B, sorry, A goes to B and B goes to E. So A goes to E will be in our, A goes to B, 1 second, R goes to down. A goes to E was already there. So, sorry, A goes to, we have A goes to B, and we have B goes to A. So we're going to have A goes to A here. Okay. So A, you can reach A from A, right? And that's that cycle happening. And so I think that's the only one you'll find there. So basically what we wind up, maybe E can reach C. Oh yeah. E can reach C also, because E can reach A and A can, okay. So anyways, I hope that you guys see that what's going to happen here, if we keep on cranking this thing around and around and around, we're going to fill this thing to the brim. R is going to get filled with the full reachability relationship. You understand that? So now, if the graph that we defined had like paths that were like 1,000 elements long, and they finally looped around again, it would eventually find them as it was doing this. And this is called, it's basically doing the evaluation of R to what's called fixed point. So it's just using the recursive definition, and it's letting R grow and grow and grow until it don't grow no more. And that means that you're computing out to fixed point. Now, what that means then is it means that it can, I mean, baby, Alex, can I go to the back of the room? Go to that room. Anyways, this might end badly. So what I'm trying to say here then is that this fixed point, the point is that you don't know, you have this arbitrary table here that's defining a graph. You don't know how deep the graph is. Now you could do it in like traditional relational algebra by saying, okay, give me all the things that are reachable within n steps. And that would just be this giant, massive like join across n tables. All right. But you never really know based on the data instance how many tables it would require. So this is actually adding to the expressivity. This idea of doing recursion inside of relational algebra is adding to the expressivity of the underlying language. Okay, I hope that people see that. Okay, so now what does this have to do with SQL? Well, now let's think about it like, okay, I think that maybe one can argue here, you can think about it, like things like reachability in a network, like things like, is there anything that was like made by North Korea that's in this product? Because the product is like, you can have a product and a subpart and a subpart and a subpart and a sub, and it can go down, basically, unbounded. You can have unbounded subpart relationships. So if you had a question of like, well, this product, is there any part of this product, anything, no matter how deep it goes, that was made by North Korea, you could actually frame that as a recursive query. Okay, so this is that's called like bill of sales type queries. What else? Things like vulnerabilities in software product. This software product uses these libraries. These libraries use these libraries. These libraries. These libraries. These libraries. These libraries. And at the base of that down there's a vulnerability. So is the software vulnerable? Yes, because it has one of its constituent parts way down deep is vulnerable. So I hope you can see that like recursion actually does wind up being something that something you want to have in your language. Now, as it turns out, in a practical case, I think that sometimes people use the recursive functionality, but a lot of times there's a way that there's other. I mean, generally speaking, what you do is you wind up writing like these insert intos, and you kind of do that in a program, and it kind of generates. So it kind of pre-computes the whole recursive relation in your own host language. So that tends to be kind of how things get done. But I can describe that a little bit later. But anyways, but it's nice to have recursion in the language. And so let's look at what recursion. Okay, I'll close without saving. Let's look at what recursion looks like actually inside of SQL. So let's do this. So now recursion. Okay. So they included it in the actual language definition. Now, this does not mean that all the engines support it. In fact, not that many engines do support recursion. But for us, we're lucky. PostgreSQL does. So here's how we define recursion inside of PostgreSQL, basically. So what it's using is using these common table expression things. So what it has, in general, I'm against these things. I think that these tend to kind of clutter up your SQL, but you actually do need them when you do recursion. So what it's doing right here is saying with recursive R from to as, and then this is that first part we had where we were just kind of copying in the edge relation into R. That's what this does right here. This is a select from that. And this part right here, doing a union, this is essentially the same expression we just had in the relational algebra example I did. But of course, this right here, down here, we have a from thing. So this is basically saying what is reachable from a particular node. So not give me the whole reachability relationship. That doesn't make much sense. It'd be like, what can I reach from state A? And it'll give that back as a correct result. Okay. So this is how you do it. You can actually do this. You can actually put this in to PostgreSQL if you build a graph representation like I did. So this will actually work inside of PostgreSQL. One of the things I was going to say about it though is that one of the reasons why, like, if you want to say like, can we do Dijkstra's algorithm with recursion? Kind of. Can we do? I mean, algorithmically, you're kind of limited with what you can actually express this way. So again, that's just yet another reason why you typically kind of just do this kind of manually. But we'll come to that again later. All right, good. So that was recursion. So now I want to move on to some other SQL aspects, and that is, one sec, right, escape. Right. Again, any questions, just put them in the chat there. Now what we want to do is we want to look at views and indexes. All right, so this is a kind of something that SQL is very it's kind of quite a powerful aspect that you don't get in other kind of data models, with the idea of having views. So what a view is, a view in the kind of traditional sense. I mean, we have two different types of view. We have a virtual view, which is the common way you're doing views, and then we have a materialized view. And actually, I am like, just to let you know, I'm very much anti-materialized views. I think there's much better ways of doing things. I think that there's a lot of downsides to materialized views, in my opinion. But they are part of the language, and a lot of people will talk about them, so we need to mention them. But I'm anti-materialized views, and I'll give you a reason why. All right, create view. So forget the materializer, just create view, give it a name, and then give it a query. Just give it a query. Okay, so it's quite nice. So create view is can drink, and can drink means that we're going to have a drinker and a beer. So the drinker is able to drink the beer if they frequent a place that actually sells that beer, right? That would make sense. Now, so we're kind of enriching the tables now with this can drink. It's like a table. It's like a virtual table. You can treat it almost exactly like a table. Of course, you can't insert into it, and you can't update it. Because notice, if you insert it into this, if I just said, oh, by the way, Jim can drink Bud, we don't know how to reflect that in the base tables to make it true, right? Because all we have is like a bar selling a drink and Jim frequenting that bar. So if we can't insert into the view in general, because there's not a unique way to reflect that back into the base tables, right? So views are limited in that sense, but it's quite convenient to have views kind of built up and defined. Okay, so now that we have that, now that we have can drink, we can actually ask a question like this. We can basically say, give me the beer that Sally can drink. What are the beers that Sally can drink, right? And then when you give the SQL processor this query right here, what it actually is doing in a view is it's going to this can drink, when it parses it, it's going to find, oh, can drink, what is that? Oh, that's a view. And what it's going to wind up doing is it's going to literally substitute in this definition here. So it does kind of like a syntactic expansion on the SQL you're asking. Internally, that's what it's doing. And that is actually kind of a very, very generalized way for it to basically handle views. All right, so they're quite powerful in that way. Now, materialized views is something where what you do is you basically tell the system to pre-compute the view. So, okay, go ahead, here's the view, but could you pre-compute it so you have all the answers ready to go? All right. Now, this is a good idea, but there's a better way of doing and that's basically this issue of like this insert into with a select query. It's a much better way, and I'll tell you why it's better. Because there's extra stuff that you actually have to do inside the materialized view to kind of make sure to kind of keep it refreshed. And the biggest problem with materialized views, and it's really kind of, it makes me wonder why anybody ever uses them, is that as far as I know that in PostgreSQL you can't do it. I don't know about Oracle. Maybe in Oracle you can, I don't know. But you cannot index. You cannot index the materialized view. Whereas a table, a base table, you can index. And then you might say, okay, Michael, but what does it mean to index? And then I tell you, okay, here's what indexes are. So without indexes, databases would be completely useless. They would be like, nobody would use them, right? They would be like, this is just kind of a toy, right? But indexes are what make relational databases for real. So index is like this data structure that uses to speed up access to the tuples of a table, given one or more of the values, okay? So it's generally not a hash table. It could be, it was historically, but what it actually is what's called a B plus tree. So the underlying underlying structure, data structure that's used is the B plus tree, which actually, if you're interested, we go over this in the advanced course. We go over this in kind of detail. All right, now here's what you do inside of SQL. Well, there is really no standard. The standard is very loose in this regard. So it's kind of, well, it's something that in PostgreSQL, you do something like the following. You'd say create index, and then you give the index a name, beer index, for instance, on beers, their manufacturer. So this is the table beers, and you're using the manufacturer. Now, what does it mean when you've done this? What this means is it means that you build up a data structure so that if you ask the query, give me the beers manufactured by Anheuser-Busch, it doesn't have to like scan the whole table to find those beers. Instead, it scans this B plus tree, it uses this B plus tree to find the tuples that are in the table that are Anheuser-Busch. Okay, so you wind up getting, instead of like doing in kind of computational complexity terms, instead of doing an ON, and where N is the number of beers search, you do an O log base, probably something like log base 300 N. Okay, and log base 300 will take a very large number and it will squash it down to something really shrimpy very quickly. All right, we know log base 2 already will squash things down, but just imagine doing log base 300. That'll really squash. So in other words, that basically means practically is it means that you can basically have these queries where you're looking for the manufacturer of the beer, and now we can have like 10 million beers, and we can practically find, because we have this index build, we can practically find, without having to scan over those 10 million beers, we can practically find the beers that are where the manufacturer is Anheuser-Busch. All right, so that's the big win for these. And then what's nice about these is these actually wind up, you can actually do them on more than one attribute. Okay, so in this case, bar and beer. So this becomes very, very useful when it comes to like, certainly comes useful when it comes to spatial queries and that kind of stuff, but it's a little bit beyond the scope here. But the idea that there's a very generalized way to kind of have multidimensional indexes. So using indexes, all right. The database engine will actually use the index. So it's the one that's going to go in and it's going to figure out which index to use. All right. Now there's something called explain analyze, which I'm not sure if we cover here. No, we don't. So if you basically say on the front of your query, you say, so you have a query, let's say select star from beer where manufacturer equals Pete's or something. And then you say out in front of that, you type in explain, analyze, and then select star from beer where manufacturer equals Pete's. When you do that, what it will actually do is it will show you in PostgreSQL, it will show you what the query plan is. And if you look in the query plan, you'll see that it's actually, you're hoping at least, that it's actually using your index instead of doing a table scan. What you do not want is a table scan, because a table scan is just like, it's gonna draw everything in. So this kind of technique of being able to have indexes on your data or your database tables, that's really kind of what makes it so that relational databases are like practical. Right? It makes it so they can be very, 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 very fast. All right. So what else do we have here about? Let me see. What are we missing here in terms of SQL? we've covered indexes, we've covered views, we've covered the base table stuff, the base query stuff. I think maybe let's see what we have time for here. Here, let me just take a little like a 2-minute pause here. I think I want to really kind of sec. This would be kind of nice for us to kind of get this played. Not sure how far we'll get with this, but one sec. All right. Again, I apologize. I'll cut this out of the video. I think it's kind of silly. Let's see, this is 36 minutes in. So just give me just bear with me for 1 second here, people. Everything slows down because I need to do this authentication now. Every time you log in, you gotta do this authentication. Come on. Microsoft Authenticator, please. Come up. Okay. Yes. Okay. Here, 1 second, people. Again, apologize for this. This is not what I like doing in Lecture. All right, 1 second here. I could just get this done. Okay, 1 second. 1 second. All right, and then we go here. We're going to do this really quick. This is good. I'm okay. So I apologize. So I want to cover this really quickly as well. Transactions. All right. So this is another big thing, a big win you get from databases. This is actually, without this, again, it probably wouldn't be practical, but since it does have this, this means quite a bit. So, so the idea then is behind databases is that what you want is you want a way to control multiple people accessing the database at once. So database systems are normally being assessed by many users or processes at one time, both queries and modifications. Okay, so but if it's just reads, if everybody's just reading from the database, that's easy because you just, everybody just does their select query. The problem comes when there are some writes, when people are doing writes. And what you get is you get what's called the lost update problem. If you don't have any type of like, okay, so for instance, like let's say that you're on an OS and you allow 2 people to edit the same file at the same time. If both, okay, if we're both editing a file and then you write the file out, and then I'm like, a couple seconds later, I made my change and I write the file out. I'm going to clock, if you don't have any extra stuff in there, and I know a lot of files, a lot of operating systems now have added this kind of stuff. But if you don't have any extra stuff there, what you're going to wind up doing is I'm going to clobber whatever you wrote out. Okay, I'm going to because you're like writing one part of the document, I was writing another part of the document. You saved that new stuff was in there, but the old stuff was still in my copy, and then I saved my copy over your copy, and we have what's called a lost update problem. So we do not want to allow this to happen in databases. Okay. So the way you handle this, and this actually is like also so this guy, Tim Gray, he got the Turing Prize for this observation. But the way you handle this is you handle this via transactions. So what you do is you wind up starting a transaction. Now, I'm sure a lot of you guys have heard of this idea behind what's called ACID transactions, as opposed to base transactions, which we can talk about later a bit. Basically, what an ACID transaction is it has to be atomic, consistent, isolated, and durable. So what that means, then it means that the whole transaction is either done or not done. So in databases, like it may be that you're going to read some account information, and then you're going to take $100 away from one account and add $100 to another account. Now, at the same exact time, I'm doing the same exact thing, but maybe in a different amount, right? And maybe I'm taking from the one account that you're going to transfer, I'm putting it back the other direction. But the point is this. The point is that one of us, if we're both going to contend over that account table, and one of us is going to get aborted. All right. The database system is going to say, because it was impossible. We got into like we got into a situation that didn't make any sense. But the important point is that these are atomic. So either yours goes through or mine goes through, or neither go through. But we can't have both of them go through and lead to inconsistency. So the idea is that a transaction will either run completely or not at all. If it's aborted, then what do you do? You rerun it. Okay. So there's kind of like ways in which becomes very, very practical. Consistent. Alex, hey, dude. Alex, can stand over there. Papa or Calvin? Stella. One second. Baby. Good boy. I think he's getting tired of hearing this database talk, which maybe you guys are too. But we're making progress here. Okay, so another thing is consistency. That is that we want to have the constraints of the database preserved between the transactions. Now, the isolated is actually the interesting one. Let's get back to that in a second. Okay, so let's go to durable first, because that's kind of the easier thing to say. So let's say that you go and you push through a transaction and you make a change to the database. And it says, fine, good, done, success. You don't ever want it so that actually gets reversed like 10 minutes later, because you were just told that you succeeded, right? So your transactions, once you're told that they went through, they're atomic and yours went through, it better be durable. Now, let's think about that practically. What that means, of course, is that it needs to be written out to disk. If it's not written out to disk, then somebody can always pull the electrical plug, and then, of course, oops, it's gone, right, forever, if it hadn't been written out to disk. So durability, to get durability, you have to write it out to the database. Now, isolation is much more interesting. It's much more deep. So the A, C, and D are usually held constant in database transactions. The isolation, however, is what wiggles. That's what you can actually change. So if you think about it, isolation, if things were perfectly isolated in the world, then we would have a database and everybody would feel like they were the one and only person working over the database. They would never feel like they can feel completely isolated from everyone else, and that would be a good thing in this case. What we'll see then is that what we get to here is we get to like the isolation level of what's called serializable. So this usually you pick kind of like there's one standard isolation level you pick, but I mean we'll cover this again because I think we're not going to be able to finish it all in time here today. But let's give it a try here. So what does it look like at the SQL level? What do these transactions look like? So what you have is there are a bunch of SQL commands that are kind of grouped together in order, and they always start with the begin statement, okay, and then they always end with a commit. All right, and that commit is like you're saying that's when you want it to get pushed through, the full transaction to get pushed through. Oops. You might also, as you're doing the transaction, you might realize that it's not, you've gotten into a bad state, or you just decide you don't want to do the transaction and you abort it. So you can actually abort it from yourself. You can just basically say abort, and that will abort the transaction. A lot of times, however, the abort will come from the database system itself. So it will actually abort you rather than you aborting yourself. So here's the kind of the example we're talking about before. Okay, assume that we have the cells at a bar is selling a beer at a certain price. And then suppose that Joe's bar sells only Bud for $2.50 and Miller for $3. Sally is querying cells for the highest and lowest charges. Okay, so this example here shows that if you don't regulate it, and you can study this and things, you wind up in a really kind of strange situation here. But if you put it into transactions, then what it does is it basically will wind up ordering things in the proper way. So this is usually how so you can actually experiment with this if you have two processes kind of touching the same SQL database. But what you want to do is you want to say like set transaction isolation level equal to serializable. You usually want to just have serializable. That's the most common one. That's the one that's the most recommended, is to run it serializable. And let's just see if I do an example here. I think that the thing I wanted to show here is just I just want us to kind of complete the SQL. See if I can do this. The only thing that you guys have to take from this lecture right now, as we've done it, is the following. Let me just text editor. Oh, where are you? Oh, there. Okay. So let's just assume we have the following. We have a database. It has account, and that account has a number and a balance, right? And we're going to have account number 1 with a balance of that, account number 2 with a balance of that, account number 3 with a balance of that. Okay, so those are the that's the state of our database right now. So now we have user number 1, and then we have user number 2. Now, let's say that we didn't have any transaction processing at all. And then what user 1 does here is user 1 says, basically, let's see, I'll say update and then I guess it's account. Set balance equal to if I want to do this here, set balance equal to 2223, where number equals 1, and then it's going, and then we're going to do another one where I say update account balance to 233, where account number equals 2. So what user 1 has done here, or tried to do here, is what they're doing is they're taking $100 from account number 2, right? See, because it's going down by $100, and they're putting that into account number 1, right? And see how that's going up by $200, right? And then at the same time, we have user number 2, who's going to basically say update. Let's do this. Okay, I'll do user number 2 is going to basically say the following. They're going to say, oh, one second. Update account to balance. Account number 1, they're going to update that to balance. They're going to update account number 3 to balance 32 22, and then they're going to update the account balance to okay, so let's see here. So we'll make this a little bit more realistic. Let's see how much time we have. Oh, we got enough time here. Okay, so this right here, this business of like, how does it know to update this to that? Let's just kind of spell that out, and that would be something like this. It will say basically select balance from account. Sorry, do what you want me to do here. From account. where number in 1, 2. Okay, so what it's doing right there, you see, this is the SQL here, where it's getting the balances of accounts 1 and 2. All right. And that's why it knows, because it's gonna do the $100 move. Oh, where's my chat? I really don't like this about. This is one thing I really do not like about the Zoom. It's just like, this is bad. Where did my chat go? Please. Oh, here it is. Yeah, somebody talk about these. Yeah, these slides. The thing is that I want to kind of be able to cover more material. I'm going to probably redo the transaction stuff because we're not going to finish it in time, but I want to at least give you a flavor. I just wanted to kind of give it like a nice wide coverage of SQL here, because I think that a lot of this is pretty straightforward. With SQL, you can find a lot of this on the net. I mean, just like kind of what is SQL and kind of how are these things. So I just kind of wanted to kind of get out in front of it here. So that was the answer to the chat comment. All right, 1 and 2, and this will be 2 and 3. Right? Okay, so now we get the balance here, and that's why we can, and then of course, in this case here, we're going to set the balance to, down to that, and then we're going to set, when we read it in here, because these other operations had happened, we got the record here of it being at 233, and now we're going to say 243, right? Because we're adding $10 to it. Or are we? Yeah. We're basically taking this case. What we're doing is we're taking. I guess this is taking. Let's see. 223. This is adding $100. It's taking from. Okay. Okay. So now I'll make a comment here. What is this actually doing? It's taking transfer. So this is by how you do a comment in SQL, by the way. Transfer $10 or 10 units, whatever, or 100 units, from 2 to 1. Okay, and then this other one here is now going to transfer 10 from 3 to 2, I believe. Okay, anyways, the ending results here are going to wind up then being, I mean, what's the ending result of the database at the end of all this? I mean, this is the starting database, and then the ending database is going to be, we can figure it out here. We can figure out what the ending result of the database is. The ending result is going to be, well, I can just kind of look at it here and say, okay, it's going to be 2, 2, 2, 3, and it's going to be 2, 3, 3, and then I'm going for the other one, and it's going to be 3, 2, 2, and it's going to be 2, 4, 3, right? So this is the ending balance. I hope that you guys all see that. I'll just kind of have that as a. So we ran 2 transactions. We had user 1 and user 2. They all did this. Now the question is this: does this make any sense? Is this like, okay? So if you basically sum the total amount of money in this database state here, and then you sum the total amount of money in this database state here, they should be equal. There should not have been any lost money running these 2 transactions. Now, if we did the following, however, we actually, so these are serial because user 1 goes first and then user 2. Okay, but if we did the following, we move this up here. Alex, hey, do. Okay, yeah, I can understand. Here, puppy. Alex, hey, come talk. Start it. Stop talking. Yeah. Okay, fine. Okay. I'll become a star. Okay. So now if we did it this way, however, if we did it this alternate way, so in other words, user 2 came in and did their read here. So they're reading accounts 2 and 3. User 1 is going to read accounts 1 and 2. And then this user here is going to then wind up doing all their business. And then this user here, then this is going to be all screwed up here then, right? Because what this is basically going to do is that'll be the same. But this one right here will basically be, so I have to put 10 on top of what? 10 on top of the original. So that's going to be, let's see. This one here goes to 233. This one here is just 233. Yeah, so 343. That's what this becomes. Right? And now we have this. So what happened here? What happened was that the work that happened here, where it had actually done the change here, this got lost. It got clobbered by the fact that the read happened here and then the write happened here. I hope that people see that. All right. So this was like really like, ouch, because what that means then, the bank does, it's not a good day for the bank, because now there's actually like the total amount of money here now, and the total money, it's like $100 is like, you know, came out of nowhere, right? So this is inconsistent. So had they done the following though, had they basically said, what would the database engine have done? Had they basically said, begin transaction, begin transaction. Okay, so now that now the database, because they said that begin transaction. Now the database engine knows they're doing transactions, right? So what happens then? This reads in this, he reads in here. This one also reads in the balances, right? And the balance in 2 is fine. But then when he goes here, at this point here, anort. The database will say anort. Okay, boom, boom, boom. All right. When he tries this, right after this command right here, the transaction processor is going to abort him. It's going to say, "Oop, no, sorry, you can't do that." So it's going to basically, this guy is going to not run all the way through. User 1 is going to be like, "Oops, I can't do that." User 2 will continue and then change the database. And then what has to happen is that user 1, if he's running as a program, especially, I'm sorry, I gotta. Okay, he commits. So now this gets committed to the database, and this guy got aborted. So what has to happen then is that he has to just do all this over again. All right. So he'll just have to rerun himself. And then there will be no anort here. He can go all the way through and do a commit. Of course, the numbers will be different, because when he does the read at this point here, he'll get different numbers. Okay. So I don't know what these are, but anyways, but I hope you guys see kind of roughly what's going on with this kind of thing. So it's really, really a useful capability to have inside the database, because what it does is it ensures that the fact that the database engine is smart enough to do this here, to kind of to basically not let things get tangled up in a weird way. All right. This is like one of the, again, like I said, this is like one of those things that makes databases very, very practical. All right. And this is, by the way, this is something that other kind of like data models have a lot of tough problems with doing this kind of like the transaction theory inside of databases is so much more advanced than it is in any other data model. Remember, the data models were semi-structured and object model, right? Those are the other kind of contending models we come up with. All right, so they have a really hard time with like transaction processing, whereas with the relational model, it's very, 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 very well developed theory and practice. Okay, all right. Well, I just thought I would cover all that, and so that was like a kind of whirlwind tour of SQL there for today. And then what we're going to get into now after this is we're going to get into like modeling. Yes, abort gets triggered. What happens is that because the database engine is watching over their shoulder, he begins a transaction, he reads in account 2 and 3, specifically account 2. That's the important one. This guy then he reads in account 2, but then he tries to write to account 2. And if he writes to account 2, that would invalidate his read here. But he started first, so he will be aborted at that point. So abort, he gets aborted. Okay. The database engine is very, very, very specific about this too. For instance, had this been like a transfer from account like 7 to or account had this been right here a transaction from account number 7 to account number 14, there would never be any collision because they're not reading the same stuff. It's not over the same kind of thing. So so it's very, very yeah, it allows for lots of interleaving, but it will also not let you go through and screw up the database. It's very, very smart about that. So the transaction processor is very, very smart. Okay, now next, what we're going to move to next is we're going to move to actually, okay, so we've done like kind of SQL kind of database, whatever. But then the question now we're going to focus on the next several lectures is, yes, fine, but how do you actually decide how you're going to design the database, the tables and all that stuff? How are you going to do that? So that will become now the focus. That's a focus. That's kind of an issue of like data modeling and normalization. Okay, so we're going to be moving on from SQL now back into a little bit more. Well, you'll see. I mean, in the next lecture. So, okay, great. Any more questions? Put them in the chat. Otherwise, I will see you guys next time. Okay. I'll stop sharing that. Yes. All right, bye-bye.